Suppose you have a state with all up, like this. Then there is a very slow process. So let's call it T slow, through which some domain forms spontaneously somewhere in the system, like this. And then there is a very fast process, because this domain then executes a random walk in this direction, in the x direction if you wish. So then there is a fast process through which this domain basically goes to the other end, and then everything gets converted to minus. Okay. And as I explained, in reality, this T slow for the Ising model is something like e to the alpha times L to the d minus 1. So if d is 2, as in this example, so it's a two-dimensional thing, then this is alpha times d divided by k dt, right? So this number, because it can be incredibly large, we also stress the point that in any big system, you actually see something like an ergodicity breaking. Because even though this time scale is finite below the phase transition, so if you take a truly infinite time scale, then of course you would see the net magnetization to be 0. But this time scale is so incredibly large that for all practical purposes, we can actually push it to infinity. This is almost like what we discussed in the first class of this lecture when we were talking about Feynman's statement that, in equilibrium, you basically say that all the fast processes have happened many times and all the incredibly slow processes could be ignored, right? So this is very reminiscent of that, right? So this is actually a very important point to keep in mind. If the opportunity arises, we'll come to this point again later in the course, but we'll see about that. Okay. So, yeah. So today, I wanted to do a slightly advanced topic, which I won't give you in your examinations, but nonetheless, it's very important to sort of briefly discuss that. And you will also see that it's part of the notes. Okay, so see, till now, what we have achieved is we know how to solve the 1D Ising model, right? We know how to solve the 1D Ising model. And in particular, we also solve the open boundary condition in the 1D Ising model, and we also learn transfer matrices and solve the periodic boundary condition in the presence of magnetic field, right? So that's something important. But the 1D Ising model has no phase transition at finite temperature. Okay. Then the second thing which we learned is how to do mean field theory of the Ising model. Okay. This is of course an approximation, but as we discussed in the last class, or I don't remember which class, as we discussed sometime in the previous lectures, this mean field approximation becomes exact when you are considering a hypercubic Ising model in some very high dimension, let's say d equal to whatever, 200, 300, something like that, because of the central limit theorem. So in the mean field theory, we assume that the fluctuations between the spins can be ignored, and that assumption basically becomes exact due to the central limit theorem when you go to a very high dimensionality. That is simply because the spin is basically talking to 2z neighbors, right? 2 times z neighbors, sorry, 2 times d neighbors, that's equal to z, right? So if d is large, this central spin has a huge number of neighbors, right? So I'm just drawing this schematically. This central spin has a huge number of neighbors, and that is why you can again use central limit theorem kind of arguments, okay? So, and the mean field theory gave us a very wonderful thing, which was that it actually predicted a phase transition. And the phase transition temperature was basically Z times J. Okay? And below the phase transition, the system sort of spontaneously broke symmetry. And above the phase transition, the symmetry of the Hamiltonian was restored. Okay, right. But I also told you that if you solve the two-dimensionalizing model, then in fact there is a phase transition again. This number changes from z times d to something more complicated. I just need to look that up because I never remember it. So due to Onsager, we know that this number is 2j divided by log of 1 plus square root for the two-dimensionalizing model. Okay? For the 3D-izing model, we again know that something like this happens, but we don't know this number exactly. The best estimate of this number is formed through some technique called Monte Carlo algorithms, which will come later on in our lectures sometime, okay? Sometime later in our lectures, so yeah. Okay. By the way, let me ask you guys a small question. I think for your generation, all of you know at least one programming language, something. It doesn't matter which programming language. But is there somebody in the class who does not know any programming language? Okay, so I assume that your silence means that everybody has at least encountered some programming language or the other, right? It's not important which one. I mean, anything is fine. So yeah, but actually, yeah, this is again an interesting thing. I mean, when we were kids, we used to learn things like C or Fortran in school and college. So I was just wondering sort of what the programming languages they teach to you guys now.
Sir, we are learning C programming this semester.
Oh, so nothing has changed from C, okay.
Yes, sir, more basic na C is basic.
Okay, very good. So anyway, C, Fortran, then I think many people these days, what is this new thing? Learn Python and things like that, right? So anything is fine, yeah. Because, when we go to this thing called Monte Carlo algorithms, of course, I'll tell you the theory of this thing. But if you write it on the computer and program it yourself, it'll be amazing for you because you will be able to see these kinds of things. Literally in front of your own eyes by doing an actual calculation, right? So of course, it'll be very nice if you write your own code and see these things, right? Then you truly see what's happening, and anyway, so we'll come to that quite a bit later in the course. Okay, so today I'll actually try to calculate this transition temperature for the two-dimensionalizing model. As I said, Onsager basically sort of did this in 1944, and this was basically one of the most important things in theoretical physics. And in fact, the American Physical Society even celebrated 50 years of Onsager's Ising model solution because it's a thing worth celebrating. But that solution in all its glory, it's quite complicated. You can actually look at Kersen Huang's book for some hints into how it's done if you want to know it. But I won't cover that in the lecture. I'll instead cover something else. Okay. And then you will see that there is another way to derive the exact transition temperature for the two-dimensionalizing model. Okay. And yeah. So if you look at my notes, which I have sent to all of you, I have, of course, given the solution to this here, but I think it needs some explanation. Okay, so I'll sort of go through that. And then you can again refer back to my notes. And if there is some problem, you can, of course, ask me again. Okay. In my notes, you will see that I have also referred to this paper. This is a famous paper by John Kogut in reviews of modern physics, volume 151, page 659, 1979. So why did I refer to this paper? Of course, it explains this 2D Ising model thing, which I'm going to talk about. But it explains many more things, okay? And this is one of those papers which is a classic paper and is necessary for understanding, what should I say? It's necessary for the reading and understanding for anybody who wants to, let's say, do physics at a more advanced level. So I encourage all of you to try to read it. Of course, in your first reading, you'll struggle through it. Maybe you'll just understand 10% of it, right? But then you try to work it out, and maybe then you'll, at the next reading, understand 20% of it, and so on and so forth, right? So, but one thing I wanted to point out, look at the title of this paper. There's something called lattice gauge theory. You might not have encountered the phrase lattice gauge theory in your education, but probably all of you encountered the phrase gauge theory in your education. Is that correct? You must have heard this term gauge theory somewhere. Is that correct?
Yes. Yes, sir.
Okay. And of course, now we are looking at spin systems, right? But obviously, there seems to be no connection between gauge theories and spin systems, right? I mean, gauge theory seems to be something which particle physicists do, right? Or high energy physicists do. Spin systems are something which seemingly condensed matter physicists do, or people who do statistical mechanics, they do. But in fact, there is a very deep relation between these two subjects. Of course, in this series of lectures on statistical mechanics, I won't cover this relation at all because there's a very advanced topic. But some simple examples of this are given in this reviews of modern physics. All that I wanted to point out is, I mean, physics is a very beautiful universal framework, and there are deep interconnections between different things. And if you learn one subject well, and then you learn the interconnection, then whatever you know in that one subject, you can immediately apply to the other subject, okay, and vice versa, right? So, yeah. Anyway, so this is just to motivate some of you to try to read this paper, okay, whenever you can. Good. So now we'll start with the two-dimensionalizing model. So imagine that you have an extremely big square lattice, right, with capital N spins. With capital N spins. I think that's the notation I used in my notes, capital N spins. Okay. Now, what we'll try to do is the low temperature expansion and the high temperature expansion of the two-dimensional Ising model. Okay. So, by the way, I think later in the day today, I'll send you guys a small assignment which will have some very obvious questions on transfer matrices. Okay, I mean, they'll be just some algebra questions, but if you just do them yourself, which are nothing more than diagonalizing some 2x2 matrices and doing some traces correctly, then of course you get a more of a hang and a practice about this method. In that assignment, of course, I'm doing the more complicated case of the low temperature / high temperature expansion of the 2D Ising model, right? And as I said, this is a slightly advanced topic. But once you know this, in the assignment, I'll give a small problem of the low temperature and the high temperature expansion of the one-dimensional Ising model, which is a much more simpler problem than the problem that we are going to discuss, okay? And then once you understand this more complicated problem, you should be able to work out that simpler problem as well, right? And then you will see some interesting things about the 1D Ising model, and it'll be very nice for you to compare, because for the 1D Ising model, you know the exact solution. Okay. Whereas these methods that I'm going to teach you, they are perturbative methods. Perturbative methods. So since you know the exact solution for the 1D Ising model, you can compare the perturbative methods with the exact solution, right? So that you can do yourself and you will learn a lot. Okay, so that's the basic idea. But for the 2D Ising model, doing this low temperature and high temperature expansion will in fact tell us something very remarkable about the 2D Ising model. Okay, good. So we'll see what it tells us. So what is the idea of the low temperature expansion? So let's start with the general idea. So the general idea is the following. Then I'll tell you the algebra. First, let me start with the general idea. This idea is the same for any low temperature expansion of a partition function for any sort of lattice model, for any model. Okay. So what is the idea? The idea is, suppose I'm at 0 temperature. Then at 0 temperature, some model may have some particular ground states, right? For the Ising model, we know that there are two possible ground states. One in which all the SIs are equal to +1, all of them, right? And the other in which all of the SIs are equal to -1. These are the only two possible ground states. So let me take a reference ground state in which all of the SIs are +1. Okay. Now you may ask, why do I take this reference ground state at very low temperature? Because, you know, I have the intuition that the 2D Ising model sort of has a phase transition at low temperature. So what that means is, if I start from one ground state, then the system basically spends its time in that ground state, right? Because there is a phase transition below a certain temperature. So if I'm doing a low temperature expansion, of course, if I start the system with one ground state, if you wish, the tunneling time required to go to the other ground state is incredibly long. Okay, right. Of course, if your perturbation tells you that this approximation fails very quickly, then you know that the tunneling time cannot be large. And in fact, that is what you will see in the one-dimensional Ising model. Because in the one-dimensional Ising model, we know that at any small but non-zero temperature, the system can just go back and forth between one ground state and the other. Because remember, as soon as you raise the 1D Ising model to a finite temperature, you can sort of create all kinds of domain walls of all sizes, right? So, yeah. But you cannot do that for the two-dimensional Ising model, not till you cross a certain temperature. Okay? Right. So the basic idea is, let's say I start with one of the ground states in one particular ground state. So that ground state is my reference state. That's always the idea. So here I start with the ground state where all the SIs are +1. This is my definition. I could have equally started with the ground state where all the SIs are -1. That's my choice. So I choose this as my reference state. This is my choice. Okay. Right. Now, for this, what is the partition function? For this, so let me actually sort of shift my energy such that the ground state has 0 energy. I shift my energy such that the ground state has 0 energy. Okay, so the partition function for this ground state is just 1. Why is that? Because you can just write the partition function as, let's say you look at the ground state that has 0 energy. Then there are some other bunch of states which have some higher energy, maybe at E. Then there are some other bunch of states which are at still higher energy, right? So this is increasing energy. So maybe this is E1, E2, and this is E equal to 0, which is the ground state. So I start from the ground state. Because I start from the reference ground state, the degeneracy is 1. Of course, there are 2 possible ground states, but I start with this particular one. So, yeah. So then, basically, the contribution of these kinds of things are just the number of microstates, the number of microstates at that particular energy times C to the minus beta, right? And then I just keep summing things like that. So for the ground state, this guy is 1, because again, I stress, I start with the particular reference state, and of course, E is 0. So the contribution of the ground state is 1 to the partition function. What is the next contribution? The next contribution is from these bunch of states, which are the lowest excitations which I can create over the ground state, the lowest possible energy that I can create over the ground state. Okay. Of course, they will come with this factor here. And then I need to calculate this factor here also, right? The number of microstates contained here, okay? Which I can create from this particular reference states. Okay?
So one little doubt.
Yes.
We have seen that for the reference state, omega E is equal to 1. But there is also exponential minus beta Eg. So
But that's exactly what I said right now. For my convenience, actually, you don't need to do that. But for my convenience, I'm just adding a constant term to my Hamiltonian such that the ground state energy is fixed to 0. That I can always do. So E0 is 0. Okay. But you don't need to worry about that. You can always pull out a common factor e to the minus beta E mod. That's just some number. I mean, okay. Yeah, you don't need to worry about that. Okay, right. So then this is the next term which would contribute in a low temperature expansion. And why am I calling it an expansion? Because your temperature is low, so beta is high. So this number is therefore a small number. This is like a perturbation, right? Then what is the next number? The next thing that contributes is these class of states, which are the next higher guys. So e to the minus beta E2 to plus dot 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 dot. This series is called the low temperature expansion for the partition function. Of course, if I can calculate this series to infinite order, then I know the complete partition function. But normally for an interacting theory, that'll be very hard to do. But I can always expand and calculate the first few terms, right? So this is what is called the low temperature expansion. Is the general idea clear? This is the general idea. If not, you can ask me. I can try to explain again. But that's the general idea of a low temperature expansion.
Sir, in this, where we have taken that low temperature limit, it is a general expression now. Is it equal to 1 plus e to the minus 10?
Sorry, your audio was not very good.
Okay, I will tell again.
Yeah.
So, is it a low temperature expansion or a general expression? Just is it equal to 1 plus?
No. Yeah. So let me clarify that. It's an expansion because, of course, if you write this thing to infinite order, it's a general expression, but you can never in practical terms write it to infinite order, right? That's the point. So these things are very hard to calculate for an interacting problem. So you can only go to few orders, and it's an expansion because each of these things is a small quantity. Why is it a small quantity? By definition, E1 is greater than 0. Sorry, by definition, let me put it like this. E2 is greater than E1, which is maybe greater than E3 and so on. And all these things are greater than 0 by definition, because I'm measuring the energy with respect to the ground state, right? So these are all positive numbers. Now your temperature is small, which means your beta is very large, right? Which means that all of these numbers are small, right? Necessarily means that. So you see, and secondly, this number, because E2 is higher than E1, this number is actually smaller than this number. So that's why in that sense, it's an expansion. Is that understood?
Okay, sir. Fine.
Okay, right. So let us try to calculate these terms, these higher order terms for the Ising.
Sir?
Yeah?
So we are accounting for the degeneracy by the omega in each term, right?
Correct.
Okay.
Correct. So now you will literally see how I count the degeneracy, right? So let's do it for the 2D Ising model. So this one is obvious because I have started from a state with all plus, right? That's my reference state. Now, can somebody tell me what is the excitation which I can create on it with the lowest possible energy? So the rule is you try to flip the minimum number of spins and try to create a state with the lowest possible energy. So what will you do? So suppose, no. So let's say don't even flip a nearest neighbor. Just you can do even simpler. You can flip a single spin. Do you agree? I
Yes,
mean,
sir.
yeah. So that's even simpler, right? So sorry, Rishabh, you said it should be 8 beta. What should be 8 beta? I don't understand. I haven't discussed anything. What should be 8 beta? Anyway, energy. No, energy is not 8 beta because energy cannot have beta inside it. Okay, so yeah. Is that clear? Okay, I hope it's clear. Energy cannot be 8 beta. I mean, yeah. Energy can either be 8 or 1 or whatever. It cannot have beta in it. So yeah. Anyway, so first things first. Let me just show you how to add this constant shift to the Hamiltonian so that the ground state has zero energy. It's very simple. I mean, the normal way in which the energy is written is just like this, right? But this is very easy to show. I'll just leave it as an exercise. And okay, for convenience, from now on, let me represent j equal to 1 for convenience. Okay. You can easily show that you can just add a constant piece to this Hamiltonian, and then the h prime that you get can be written like this. Where this guy is, of course, the Kronecker delta, which is +1 if both Si and Sg are equal to each other and is 0 otherwise. Okay. So, of course, if you have a ferromagnetic type of bond, right, then this energy is basically 0. Right. So, if you have two bonds, if you have a nearest neighbor bond where Si Sj is equal to +1, then this energy is 0. Whereas if you have a bond where Si Sj is equal to -1, right, then of course you will see that the energy is 1 here, and then there's a factor of 2 here, right? So the energy counting is correct. So the energy counting, yeah. Yes, sorry.
Shouldn't there be a minus sign in H equal to minus J sum over
No, sorry. Why do I need a minus sign? This is my definition. I think. Oh, I see. You're saying this.
Yes.
I see. Yeah, okay, yeah. There is a minus sign. That's good. Yes. Okay. Good. Thank you. Yeah. Okay. Good. So by this definition of energy, a ferromagnetic bond has energy 0, whereas an antiferromagnetic bond has energy 2. So it has a higher energy. Right? So that's absolutely correct, because in this definition, the ferromagnetic bond has an energy -1, whereas an antiferromagnetic bond has an energy +1. So the difference is again 2. So you see the difference is 2 here. So I have changed nothing in my Hamiltonian, right? I've just shifted it. That's it. Okay. So that's easy. Good. So now let me flip a single spin in a big lattice. So there's some very big lattice with capital N spins. I start with a reference state. So any bond like this, where it's just drawn by a simple line like this, it means that it's a ferromagnetic bond. Now let's say I choose a side here, maybe this side, and I flip this spin. Then I hope it is clear to everybody that these 4 bonds become antiferromagnetic, whereas the rest of the bonds are still ferromagnetic. Is that clear to everybody? I hope if anybody is confused, ask me or I'll go on.
There are all the bonds here ferromagnetic from before.
Yeah. Because you remember, I am just changing one single spin on the reference state. In the reference state, all the spins are +1, right? See, that is the point, right? All the spins are +1 in the reference state. I'm just choosing one spin here and just making it -1. Okay?
Okay.
Yeah. So then this guy is -1, this guy is +1, this guy is -1 +1, this guy is -1 +1, -1 +1. So these 4 bonds are antiferromagnetic bonds, right? Because there is one -1, one +1. So Si times Sj is -1, right? Whereas all the other bonds are, of course, ferromagnetic, right? Because Si times Sj is +1. Okay. So that's how I just keep track of the energy. So the energy cost above the ground state is simply 4 times 2, which is 8. Okay, that's the energy cost of this particular state. Now I have chosen to flip this particular spin, but I could have chosen to flip this particular spin and still the energy cost would have been 8, right? Or I could have chosen to flip this spin, right? And so on. So the degeneracy of these class of states is
NC1.
well, it's just n. Okay, yeah, which is NC1. Okay, fine. Right. So the degeneracy is n. Okay. So the next term in the partition function is this. Everybody agrees with me that this is the next term in the partition function when I do a low temperature expansion. Is that okay?
So in total there are n number of such,
Spins. Yeah, n number of spins. As I just now said, I will assume a very big square lattice. I'll assume a very big square lattice. And in that very big square lattice, there'll be n lattice sites. N lattice sites. Okay, that's what I'll assume. So, okay?
Yes, okay, sir.
That's true. We are ignoring the concepts of edges because they will just give some small corrections to this expression. Yeah. So you can just imagine that I'm doing it in an almost infinite lattice, and this n is extremely large, and I'm just ignoring the edges or the surfaces. Okay. I mean, I can be more careful and also do it in a finite lattice. That is not a problem. But I think if you think of it in a extremely big lattice, that is slightly simpler. The algebra is slightly simpler. Okay, so yeah. Is that okay? Okay, good. So now let us look at the next term. The next term is more interesting. See, with a single spin flip, that is all I can do, right? So the reference state is what? The reference state you can think of as 0 spin flips, right? In some way of thinking, right? Then the next guy is 1 spin flip, right? Then obviously the next guy would be 2 spin flips, right? 2 spin flips. Now here, there is a very interesting thing. You see, if you flip 2 spins, can somebody tell me in general how many antiferromagnetic bonds would you generate? If you just take 2 spins at random and just flip them over the reference state, usually how many antiferromagnetic bonds would you form? What is the answer to that? 8. That's correct. That's absolutely correct. But there are some processes in which you break a smaller number of antiferromagnetic bonds. They cost less energy. So you need to account for that first. You understand, right? Because you need to group terms which cost the same amount of energy, right? That is the important thing, because this thing, 8, beta, or whatever, is decided by how much energy some process costs. So you need to club all processes which cost the same amount of energy together, right? Now, if you take 2 distant spins and just flip them, of course it breaks 8 ferromagnetic bonds and converts them into antiferromagnetic bonds. So that cost is 16 times 16, right, with respect to the ground state. So you will sort of get a factor of e to the minus 16 beta. But actually, there will be some processes which cost lesser energy than that. So we need to take into account those before that, right? Okay. So let me tell you that there is a process which costs 2, 3, 4, 5, 6, 7, 8. Okay, let me count. So there is a process which actually only costs 6. Yeah, now you have the benefit of my notes, but anyway, 6 broken bonds. So how do I generate such a process? So let's say again I choose any spin and I flip it, right? So maybe this guy becomes -1. Now the trick is I choose any of the 4 nearest neighbors of this. So of course this guy has this as his nearest neighbor, this as his nearest neighbor, this as his nearest neighbor, this as his nearest neighbor. So let me choose this one as his nearest neighbor. This is also -1, right? I flip this guy also. So okay, I choose one of the nearest neighbors and I flip this guy and this guy. So both of them become -1. Okay. Then the point is, let us look which of the bonds are antiferromagnetic. Of course, this bond is antiferromagnetic. This bond is antiferromagnetic. This bond is antiferromagnetic. This is antiferromagnetic. This is antiferromagnetic. This is antiferromagnetic. Because only these 2 spins have changed to -1. Everything else is still +1. But of course, clearly, this bond is not antiferromagnetic, right? Because this is -1, this spin, and this spin is also -1. So it's still a ferromagnetic bond because Si times Sj is +1. Okay? Therefore, I have given you a situation where you have only generated 6 antiferromagnetic bonds. So of course, delta E is 6 times 2, which is 12. Okay? Therefore, the energy factor due to this is e to the -12 beta. And can somebody now tell me the degeneracy of such processes?
2n.
Why is it 2n?
So first of all, we need to select a site that can be done in NC1, and
Which
now
is N?
I can, which is N, and now I have to put the second spin in the in out of 4 possible 2 way. Out of 4 nearest neighbor, I have to place one the second spin, but the placing it to the right or to the left is equal. So I get 2 from there. So therefore.
Okay, well, anyway, hopefully you guys have understood what the argument is. Basically, I think what you're saying is that naively you would have said that the number is 4 times n. But the point is that if spin 1 is the neighbor of spin 2, that's the same as saying that spin 2 is the neighbor of spin 1. So there is a correction of half, which is 2n. So there's a 2n. Okay?
Yes, sir. Yes, sir. That
Okay, so the partition function is 1 plus n times e to the -8b plus 2n times e to the -12 plus ... Does everybody agree with this expression so far? Now we'll come to the more interesting case of delta E equal to 16, which is 8 times 2. Okay? There, we'll see that there are 3 possible processes with their own degeneracies. See, I need to calculate this thing correctly, right? So that's why I'll see that it's good to subdivide this thing into 3 possible class of processes so that I can count this thing correctly. Okay? It's a counting exercise now. If I count it correctly one way, that's fine. If you count it correctly the other way, that's also fine, as long as the final answer is correct. Okay? So let's see how to do that. Okay? So one possibility is the following, which I think in my notes, I call it class A. So one possibility is the following. Let me just... So, you see, how will you get 16? Normally, if you choose 2 distant spins, then the answer is 16, right? Because this breaks 4 bonds and this breaks 4 bonds. However, the interesting bit here is that you can actually show that there are some 3-spin processes. So you actually flip 3 spins on the reference state. And again, you will only break 8 bonds. In fact, there are some 4-spin processes also where you choose 4 spins and flip them, which again breaks only 16 bonds. So you need to count processes where you flip 2 spins, processes where you flip 3 spins, and processes where you flip 4 spins separate, right? And then you get this degeneracy correctly. Of course, all of them have the same delta E. So you don't need to worry about this factor. Right, but for the counting, you need to, of course, worry about these 3 processes separately. Okay, that's the logic. Okay, so let us think about processes where I need to flip 3 spins together. Then you can show that if the 3 spins are nearest neighbors of each other. That's the important statement. So you select a spin. Let's say you select some spin, and then the next 2 spins are nearest neighbors of this particular spin. Okay, so whatever spin you select, let's say I select this spin, then I select another spin, this should be a nearest neighbor of that. Then the next spin I select should also be a nearest neighbor of that. So these 2 crosses should be a nearest neighbor of this circle. If you do that, then you can satisfy yourself and show that you only break 8 bonds with 3 spin flips. If you do anything else with 3 spin flips, you can also show that you break more than 8 bonds. Please try to work this out yourself at your leisure and make sure that you understand the statement. Okay? So let us do one such process. So maybe I select this spin, and maybe then I select this spin as its nearest neighbor, and this spin as its nearest neighbor. So this guy becomes -1, this guy becomes -1, this guy becomes -1. Everything else is still +1. So now let us carefully insert the antiferromagnetic bonds. Clearly this is antiferromagnetic. Clearly this is antiferromagnetic. This bond is also antiferromagnetic. This bond is also antiferromagnetic. Right? This bond is also antiferromagnetic. This bond is also antiferromagnetic. Now see, this side is still +1. So that means, let me erase this bit. Oh, sorry. Yeah. So that means that this bond is antiferromagnetic. This bond is also antiferromagnetic. But that's it. Because you see, this bond is ferromagnetic still, because this is -1 and that is -1. So the sum is still, the product is still +1. This is also ferromagnetic, right? So now let us count the number of antiferromagnetic bonds I've generated. 1, 2, 3, 4, 5, 6, 7, 8. So that's it. So 8, right? So this factor is correct, 16 times beta, right? Now the question is, what is the degeneracy of this process? So this is actually an interesting problem. So can somebody tell me what is the degeneracy of this process? This 3 spin process, which I just showed you. Of course, you know the answer from the notes, but you need to explain to me.
The 6N?
Yeah, of course you know the answer, but as I said, you need to explain.
Okay, I got it. Okay, first of all, I need to select one site. That can be done in n ways. Now I have 4 neighbors of that n that site. So I need to choose 2 of them. So I can do it in 4 choose 2 ways. So 6 into n, so 6n.
Sorry, I did not understand. Sorry, I did not understand.
Sorry for. First, I need to pick a particular site. That can be done in n ways.
If I pick this, okay, fine. I pick this.
Okay.
Yes.
Then I can do it in n ways. Okay.
Okay.
For a particular site, there are 4 neighbors.
Okay. Good. Then.
Out of 4 neighbors, I need to choose 2 neighbors.
Okay. Yeah. So that's 4 choose 2.
That's 4 choose 2. So 4 choose
fine.
n is 6n.
Okay. Yes. So that's correct. So the degeneracy of this process is this. Okay. So that's the degeneracy of class A. These processes. Now comes class B, where I'll flip 4 spins. In fact, after flipping 4 spins, we will see that you actually get again 8 bonds. So how do we do that? Let's see. So I again take a very big lattice. And then I choose the 4 spins that I want to flip at the corners of a elementary placket of a square placket like this, at the corners of a square placket like this. So I make this -1, this -1, this -1, this -1. So clearly this bond, this bond, this bond, and this bond are still ferromagnetic, right? The only antiferromagnetic bonds are this, and this. Okay? So 1, 2, 3, 4, 5, 6, 7, 8. Okay, right? So again, therefore, it's e to the -16 times beta. And now, what is the degeneracy of this process? This is what do you think is the degeneracy here? So the degeneracy of this process is, of course, the number of ways in which you can choose a square placket. What are the number of ways in which you can choose a square placket for a big square lattice with n sides?
So n by 4 C1.
So what is that final number? Yeah, so what is the final number? Yeah, so I mean, you can compute 4C1. N. No, 4C1 is not. No, sorry. You said N, then what did you say? No, Tunushi, you said something, right? So
So n divided by 4 C1.
this. But this is equal
Yes.
to what? What is 4C1? 4 factorial divided by 3 factorial, so that's this.
No, sir, I didn't say this. I said n divided by 4. The number is n divided by 4. Now I have to take C1 of this n divided by 4.
Oh my god, that's okay. That's too complicated for me. Just tell me the number. Sorry. I'm lost with your notation, but just tell me the number. What is the final number? Tell me the number. I mean, you can compute all these factors in your head and just tell me some number times n, right? So what is the final answer? Just tell me that.
So 4n.
4n. No, that's not the final answer. No, that's not right. What is okay? So you see, this is okay. Yeah, Rishabh, it should be n. But can you tell me why it should be n? Okay, that's brilliant. 4n divided by 4, which is of course n, but that does not tell me the logic. But okay. Anyway, hopefully you guys understand it. I mean, this is brilliant. So n is of course 4n divided by 4, which is also 8n divided by 8. So which is also 7n divided by 7. But okay. I mean, that does not answer my question, right? But okay, I mean, yeah, hopefully you understand. It's okay, yeah. So hopefully you understand this. In a big square lattice, the number...
It's approximately n, not exactly equal to n.
No, for an infinite lattice, it is exactly equal to n, plus some surface corrections that we ignore. Yeah. So it's exactly equal to n plus order 1 by n terms. Which I can ignore for a very... So the answer is very simple. Let me just tell you my logic. I mean, see, this is the funny thing about counting. So when we think of probabilities or countings and things of like this, all of you would agree with me that each individual has a completely different and individualistic way of counting, right? I think all of you would agree. All of you would agree on that, right? So of course, the ultimate aim is to arrive at the correct answer properly. But I'm sure that if I give you these counting or probability questions, each of you would think differently, right? And I would think differently, and it's very hard for me to convey those logics. I mean, different people just think differently when they are counting things in their head. That's it. So this is something I've noticed. But anyway, my logic is this, which is the following. Suppose you mark any side like this. From this side, you could have drawn 4 squares. Either you could have drawn this square, or you could have drawn, sorry, I have already drawn some square here. Please ignore that. Let me use a different color. So you could have drawn this square, or this square, or this square, or this square. These 4 squares, right? But you see, so one point naively seems to generate 4 squares. So naively you would say 4n again. But you see, if I take this point again, I would again have generated this particular square, which I've already generated. And you can just think about it a bit and you will see that you're overcounting everything by 4. So it's actually, you need to divide by 4. Or another way of saying it is, you choose a spin and then you just choose that you go to the top right quadrant. That's your choice. You could have chosen top left or bottom left or whatever. I choose top right quadrant, and that square is uniquely associated to this point. And then again, the counting is n. Okay, so that's the logic. Okay? So yeah. So of course, the degeneracy of this process is therefore n times e to the minus 16 beta. Okay? Now comes the final process, which is the most obvious process, where I flip 2 spins and create 8 bonds. So there, the logic is very simple. Suppose you select 1 spin. Okay, suppose you select 1 spin and you flip that. Then the next spin that you select cannot be this spin. Also, it cannot be any of its nearest neighbors. Because if you remember, if it's any of its nearest neighbors, then you actually only break 6 bonds, not 8, right? So it cannot be this spin or any of its nearest neighbors. So you have excluded 5 spins from the next choice of the spin. So the final answer is n times n minus 5 divided by times e to the minus 16. This is the degeneracy. So just to show you a process, maybe I choose this spin, maybe that spin, and I flip them. Then obviously, these are the bonds that I create, like this. Okay? These are the bonds that I create. Okay, and the degeneracy here is this. This. Okay. Right. Okay, so basically, if you look at the entire partition function, now if you want, I can reinstate that constant shift that I did at first. Excuse me. This constant shift actually just introduces this factor. Remember, I shifted the ground state energy so that it went to 0. If you want, I can just correct for that, and that introduces this factor on the left hand side. The right hand side is this. So hopefully I've done my counting right. This you can just try to see yourself. Okay. Yeah, hopefully this is all right. And higher orders, plus higher orders, right? So this is the expression for the, of course, we have only calculated it till e to the minus 16 beta. And this is the high temperature expansion, low temperature expansion. Now, there is a way to automate this counting by writing a clever computer program. And in fact, at the time, Kogut wrote his article in 1979, and during that time, people could already calculate this term, e to the minus 152 beta. Sorry, I need some water. People could already calculate this term. Now with modern computers, people can go even higher. Okay, see, I mean, till this order I could do it by hand, but obviously you understand that if I go to even higher order, then the number of graphs and counting that I need to do is more and more cumbersome. So basically you need to write a computer program and that computer program does something called symbolic manipulations, and it gives you these sort of factors exactly. Okay, so right. So this can be done, but let me just just show you this much where I can just do everything by hand. Okay, so this is the idea of the low temperature expansion. Is that clear? Okay, so this is the kind of series. I have, of course, not calculated the higher order terms. Okay, so yeah. Okay, so now let me carry on and show you the high temperature expansion. But before that, let me actually tell you something important in the Ising model. So in the Ising model, suppose you could calculate this term to some very high order, right? This is a series after all. Because it's a series, you can in fact compute through various ratio tests and things like that, the radius of convergence of the series. Okay. And if you do that for the 2D Ising model, in the 2D Ising model, so this is t equal to 0, there is a TC. Then you see, you're starting this series from here because it's a low temperature expansion. No matter how high you go in this series, you can never extend this series here after TC. So the radius of convergence has to stop here for this series. Okay, that's an important statement. Is this clear to everybody? Why this is so? Or I can try to explain again. Sorry?
Can please repeat this part?
Oh, so you see, this is a series, right? This is a series that you got, right? Now taking this series, let's say you could calculate this series to a very high order, because you know that each term of this series to a very high order, you can estimate the radius of convergence of the series. Okay. If you try to do that, what I'm saying is, you will find that the radius of convergence is always bounded by this temperature Tc. You cannot extend this series to any temperature which is higher than Tc. No matter how many terms you keep in this series. So this is a series, right? You give me your favorite temperature. You give me your favorite temperature. I'll put this temperature in. I'll compute the answer till a certain order, and I'll just calculate everything from that, right? Because once I know the partition function, I know most other things, right? That's the usual way. I'm claiming that if I give you a temperature here, which is above Tc, no matter how many terms you know in the series, you can never compute what is happening here accurately. You cannot extend this series expansion to this side. That's what I'm saying. You cannot analytically extend this series beyond Tc because there's a phase transition.
So why is it so, sir?
Why is it so? Because there's a phase transition. So remember,
mathematically, why is it so?
No, I'm saying mathematically why it's so, right? You need me to, okay, I need to make more than one sentence to answer that, right? So, yeah. So, the reason it is so is because if you remember, when you calculated the free energy, well, we didn't calculate it for the 2D Ising model, but the point was that when we encounter a phase transition, we said that there are some singularities which happen in the free energy or in some of its derivatives, right? So basically, that means that you cannot write an analytic function here in a series expansion, which can be extended on this other side, because you're crossing a singularity in a function here. That's the mathematical reason. I don't know if it's clear to you, but that's
got it, sir. Got it.
Okay, fine. So, right. In fact, if you do this series expansion for the one-dimensional Ising model, you will see a remarkable thing. You will see that the radius of convergence would be 0. Why? Because for the one-dimensional model, immediately when we raise it to any finite temperature, the reference state completely melts because domains of all possible sizes arise. So if you repeat this exercise, for the 1D Ising model, where actually it's easier to calculate many terms in this series because the geometry is much easier in the one-dimensional case. Yes, of course. Yes. Free energy. Free energy. Yeah, that's correct. So actually you raised a correct point. I did not want to go into that, but since you raised this point, let me answer it. You're absolutely correct. What you should do is you should take the Z, calculate it till a certain order, and then take the log of Z, and actually then analyze the expansion of that. That's actually correct. Yes. Okay. So yeah. But log of Z is related to the free energy. Okay. Is that okay? Yeah. Okay. So if you do this exercise for the 1D Ising model, you will actually see that the 1D Ising model has a 0 radius of convergence. Okay. For the low temperature expansion. So this is a very interesting point. What does it tell you? It tells you that if you are at a temperature which is here, so let me mark it with red, here. So this is a low temperature, right? So what that tells you is maybe you need to keep the first few terms in this series. Maybe the first 1, 2, 3, 4. Maybe the first 4 terms in this series, which is what I've shown. Let's say you go here, very close to TC, but still on the low temperature side. Low temperature meaning still on the left of the phase transition. Then maybe to get the accurate answer, maybe you need to take the first 2000 terms of this series. But that's okay. Maybe if you go here, you need to take the first 20 million terms of this series to get a very accurate answer. Maybe you demand a 1% accuracy in your answer, right? So maybe you need the first, 20 million terms or something if you go here. But my point is, if you go here on the other side of TC, so this is TC, this is TC. If you go on the other side of TC, even if you calculate the series to whatever order you want, 1 million, 2 million, 1 billion, 2 billion, 3 billion terms or whatever, you can still not describe the physics of this point accurately. That is the point, through this series expansion. Okay? That's the important thing. Okay. Because you're crossing a singularity in the free energy. So now let me go to the high temperature expansion. So as the name suggests, the high temperature expansion will try to build a series expansion, but from the other side, as the name suggests, right? From the other side. Okay. Right. So let's go on. So high temperature expansion. Good. So now let's look at that. And let's keep this expression in mind. This is the low temperature expansion. So let's look at the high temperature expansion. For the high temperature expansion, I just look at the partition function and I need to introduce some tricks. For the Ising model. So the first trick is the following. This object, Si times Sj, can only be +1 or -1. And I'm dealing with exponential beta times that kind of an object, right? Because you see, this thing is nothing but a product of many such exponentials, right? This is nothing but a product of many such exponentials. So I'm dealing with these kinds of objects. When I deal with these kinds of objects, this is obviously an exact statement. When this variable is +1 or -1, this is by definition this. This you can just check very easily. Okay, by definition. If the variable is +1 or -1. This is not true in general. It's only true if this variable sigma is plus 1 or minus 1. Okay. Therefore, I can just write the partition function as sine hyperbolic beta. Okay. Okay. For a lattice with capital N number of points, for a square lattice with capital N number of points, can somebody tell me what is the number of nearest neighbor bonds in such a lattice? Is the question clear? So if you have a big lattice with capital N points, square lattice with capital N points, what is the number of nearest neighbors of such a lattice? Can somebody try to tell me? I mean,
So 4n divided by 2.
4n divided by what?
2.
Which is what?
2n.
Okay, thanks. Yeah, that's correct. So it's 2n. Yeah. Okay, so basically there are 2n nearest neighbor bonds. Therefore, I can just rewrite this expression as and hyperbolic beta. Okay, right. Now, what is the small parameter in this expansion? So let's stare at this expression a bit carefully. So when temperature is large, beta is small. When beta is small, tan hyperbolic beta, which is proportional to beta when beta is small, is also a small number. So tan hyperbolic beta goes to 0 as, so sorry. So this is the small parameter, tan hyperbolic. Now, how do I think about this now? So, okay, so this is the fun part. You see, look at this thing. This is a product of many, many terms, right? This is a product of many, many terms. So it's almost like 1 plus S1, S2, tan hyperbolic beta, 1 plus S2, S3, tan hyperbolic beta. Let's say I'm just drawing some, whatever, S3, S4, tan hyperbolic beta, and so on, right? So when you write the right-hand side, you can just do an expansion of this, and each term is basically either has this factor 1 on the nearest neighbor bond, or this factor tan hyperbolic beta, right? That's how you take products, right? That's literally how you take products. So one possibility is I take this 1 for all 3. So that's 1 times 1 times 1, so that's 1. The other possibility is I take S1, S2, tan hyperbolic beta for this guy, 1 for this guy, 1 for that guy. So of course the product is this thing times 1 times 1 and so on. Right? So this is how you take products in general, right? And you just write a sort of an expansion on the right hand side. Okay. After that, you need to take this trace. After that, you need to take this trace. Now, the interesting thing is, even though this product has many terms on the right hand side, not all the terms would survive. That's the important thing. So let's look at the simplest term. The simplest term is, of course, 1. So each of the nearest neighbor bonds just contributes 1. So see, there are lots of nearest neighbor bonds, and I can again think graphically. So when I want to say, I think, when I want to say that I want to think graphically about this, then what that means is that, let's say these are the lattice points. If each bond contributes 1, then I don't literally draw anything on that bond. Okay, suppose this bond contributes 1, this bond contributes 1, and so on. I don't draw anything on that bond. I just leave it empty. If a particular bond contributes a tan hyperbolic beta, I maybe draw something there. Okay, maybe let me use a different color. Maybe I use this color. Okay, so maybe if this bond contributes a tan hyperbolic beta, I draw this color, which means that all the other nearest neighbor bonds contribute 1. Okay, so now let's look at the simplest case. The simplest case is when all the bonds just contribute 1. So this lattice is empty. I haven't shaded any bond. So what does that mean? So the contribution of that term to the partition function is 1. What is this guy? What is the right hand side? What is the right hand side here?
So 2n?
2n you said? Sorry, you said 2n, is that correct?
2n.
2 to the power n.
The answer is actually 2 to the power n. 2 to the power n. Okay, anybody who does not understand this statement, please try to understand this at your leisure. This is very, very important. Okay. The answer is 2 raised to the power n, not 2n. Okay. Fine. Now, what is the next simple class of terms? Next simple class of terms is maybe I pick one particular bond and just shade it. And then, of course, maybe I call this S1 and this is S2. Then, of course, I need to do this giant sum. And of course, the term here is S1, S2, tan hyperbolic beta. Can somebody tell me what is the answer of this thing? Yeah, Rishabh, you're correct. Yes, that's true. But yeah, your mic is not working, so I cannot ask you for the logic. But can somebody tell me why this term is 0? No, that's correct. But why this term is 0? I mean, how do you see that this term is 0 in particular?
So because S1 is 2 can be either +1 or -1.
Yeah, so if no, you're of course right. So, but how will I show it algebraically? Algebraically, it's very easy, right? I mean, of course, all of you are saying the correct thing, but you can just decompose the expression like this. Yeah. And the rest of the sums, S3 and on, they don't matter because anyway, they just look at this guy. But this guy is, of course, 0. This guy is also 0. And therefore, the entire thing is 0. That's it. Similarly, if I draw something like this, then what is it on the right-hand side? On the right-hand side, you get S1, S2, S2, S3. Let's say this is S3. Tan hyperbolic square beta. So S2 times S2 is what? 1. So I can just ignore this. So this is S1 times S3. But by the same logic as in the previous line, this is also 0. Okay? Similarly, if I do this, then of course you will get S1 times S2 times S2 times S3 times S3 times, let's call it S4. But then that is equal to S1 times S4 times tan hyperbolic beta raised to the power 3, and that thing is again 0. However, now let me look at this guy. This is interesting. This is S1 times S2, S2 times S3, S3 times S4, S4 times S1 times tan hyperbolic 4 beta. But you see, S2, S2 gives 1, S3, S3 gives 1, S4, S4 gives 1, S1, S1 gives 1. So therefore, this term won't contribute 0, right? This term would again contribute tan hyperbolic raised to the power 4 beta times 2 raised to the power n. Okay? This will again contribute that, right? So the leading non-trivial term is therefore plus higher order. Is this clear to everybody? Why this is the non-trivial term?
The last line, can you please repeat?
Which line?
The one which you just showed, Z cos hyperbolic beta.
This one.
Sir, this yes, sir. From this, how you got this next line?
Oh, because you see, I mean, look, if I look at this process, then what is this process? If I just write it down, this is S1, S2, S3, S4. So basically, if I write it down and then take the trace over all the spins, I'll get a 1. This 1 you understand because I have done S1, S2, S2, S3, S3, S4, S4, S1, right?
Yes, sir.
Times tan hyperbolic beta. But when I do this, I just get tan hyperbolic beta raised to the 2n. Now, what is the degeneracy of such squares? How many times, how many unique squares can I place on my lattice like this? Of course, the answer is again n.
Yes.
Right? So this is the full answer, right? That's it. Because see, I've taken this part here, and this part was anyway there. This part was anyway a common factor, right? Remember? Because we pulled out this part here, right? So this I take on this other side. Okay?
Okay, sir. Here.
Yeah. Good. Very good. So now, similarly, you can do the rest of the counting. Okay? But now, let me show you why the counting here and why the counting in the low temperature expansion are related term by term. Okay, let me just show you, and then actually maybe in view of the time, let me show it to you in the next class. So maybe tomorrow in the tutorial at 11:30 or so, I'll send you another Google link. Okay, and maybe we can just briefly discuss this and end this part. And yeah, okay, so let's actually do that. Maybe that's the better thing. And in the night today, I'll try to send you a sort of a assignment so that you can get a bit of a practice on the transfer matrices. And those questions will be very easy. As if you can diagonalize these 2x2 matrices, which we learned, then you should be able to get all the expressions correctly. And then, yeah. So, and maybe there'll be one other question about this expansions. So, on the 1D Ising model. So, we'll see. So, yeah. So, this is what I maybe wanted to say. So, I'll continue with the high temperature expansion in the next class because I don't want to rush through this bit. Okay. So, yeah. So, anyway. So, if there are some immediate questions, you can ask me now. Otherwise, tomorrow around 11:30, we'll continue this discussion. Okay. So okay. If there are no immediate questions, then maybe that's it for today. Okay. So yeah, I'll continue in the next lecture, and then we'll see a very interesting property of the 2D Ising model, which will allow us to calculate the transition temperature. Okay. So that's it for today. So see you guys tomorrow.